Well, good afternoon, colleagues, students, friends. It's wonderful to be able to host an in-person event at our institute. It has been a while since we've done it, so we are delighted to welcome you all, and especially delighted to welcome our guest speaker this afternoon. So before I have the pleasure of introducing Professor Edwards, I'm Debjani Ganguly, a literary historian and the director of the Institute of the Humanities and Global Cultures, the host of this event. And our talk today and our event today is actually part of a year-long talk series on the theme of futurities that we began last year and will continue through this year. The series features humanists, scientists, writers, artists, and policy experts who explore existential questions about our unfolding futures. And our key question, I guess, our focus is a visualization of possible futures in the age of technological immersion and climate change. That's been our focus in the series. And many of us have heard the Metaverse CEO, Mark Zuckerberg, issue a rather ominous call to his employees, live in the future, as the company pivoted from the collapse of its social media brand and embraced virtual reality and artificial intelligence. The IPCC's mega-scale models predict catastrophic climatic shocks that await us at the end of the century should we fail to limit global warming within the range of 1.5 or 2 degrees Celsius above pre-industrial levels. So reckoning with global warming and the overshoot of other planetary boundaries is in some sense also to reckon with future reals, what we literary historians call future reals, a mode of hyperrealism of what is to come inevitably, irrevocably. Science fiction has captured such future reals for decades now. Based on hard scientific data, Dale Pendle's novel, The Great Bay, for instance, published in 2010, begins in 2021 with a worldwide pandemic followed by the gradual rising of the seas. And his imaginative storytelling focuses on California. A great bay forms in California's Central Valley and expands during a 16,000-year period. In fact, one might say that the idea of the Anthropocene itself relies on a science fiction conceit by inviting us to look at our present through the eyes of a future geologist studying the Earth's strata hundreds of thousands of years hence. So vistas of futures pregnant with promises of infinite growth and human flourishing appear to be vanishing as fast as Arctic ice. So what might the limits of our current risk modeling exercises be? Predicated in some circles as they are on geoengineering marvels and on a techno-optimism. So a fundamental shift, as many of you know, in the lexicon of existential catastrophe in our time is the displacement of the idea of the human as a sovereign agent by large biophysical, geological, and technological forces. And our runaway techno-scientific and socially engineered systems appear to have overtaken, in some senses, our ability to control them and their runaway impact on our Earth system. Anthropocene, as this new geologic phase of our Earth system is called, has been called profoundly technospheric by Peter Huff, who basically is an engineer, and he does geoengineering. And he formulated the idea of the technospheric planet and says that it represents a new stage in the geologic evolution of the Earth. So few scholars are more suited to addressing the work of such technospheric global infrastructures than our distinguished speaker this afternoon, Professor Paul Edwards. Professor Edwards is one of the world's renowned historians of science and technology and William J. Perry Fellow at the Center for International Security and Cooperation at Stanford, where he also directs the Stanford Existential Risk Initiative. This initiative is dedicated to mitigating existential risks such as extreme climate change, nuclear winter, global pandemics, and other risks from synthetic biology. This is going by a website, and risks from advanced artificial intelligence. So prior to Stanford, Professor Edwards spent 20 years at the University of Michigan, where he's currently Professor Emeritus of Information and History. his work focuses on the foundational power on history, politics, and culture of knowledge and information infrastructures, and on the foundational power of such infrastructures to generate comprehension about large questions around environmental security in relation to climate change, Anthropocene risks, and nuclear winter. His exploration of how computer modeling far outpaces empirically based knowledge on the global climate is an indispensable resource for comprehending the complexity of climate change. As he writes in his monumental 2010 book, which I think we've all read and reread many, many times to make sense of our times, published from MIT Press, entitled A Vast Machine, Computer Models, Climate Data, and the Politics of Global Warming, he says, everything we know about the world's climate, past, present, and future, we know through models. So Vast Machine was awarded many prizes, including the Computer Museum History Prize from the Society of the History of Technology and the Louis Batten Award from the American Meteorological Society. The Economist named the book of the year in 2010. A book of the year in 2010. Okay. Professor Edwards is also the author of The Closed World, Computers and the Politics of Discourse in Cold War America, that explores the mutual shaping of computers, military strategy, and cognitive sciences from 1945 to 1990. It won honorable mention for the Rachel Carson Prize of the Society for Social Studies of Science. His work has been funded by many prestigious bodies, such as the National Science Foundation, Sloan Foundation, and many other funding groups, including the Guggenheim Foundation. So with Janet Verthesi, Professor Edwards co-edits a book series from MIT Press. Again, many of you would be familiar with this series, called Infrastructures. And he has recently served as the lead author for the 6th report of the IPCC, that is the Intergovernmental Panel on Climate Change, published in 2021. And his current research concerns the history and future of knowledge infrastructures, as well as work on the history of climate science and other large-scale environmental data systems. His talk today is entitled Technology Eats History, Technometabolism and Time in the Anthropocene. Please welcome Professor Edwards.
All right, great. Zoom people can hear me too, I think. Okay, that was a lovely introduction. Thank you. I do have to make one other correction. I was not the lead author, I was a lead author. There were 235 others, so it's a yeah, so let's see. This happened before. We have some delay here with control of my slides. I'm going to talk about time in the Anthropocene. Time is not something people are very good at thinking about. Oh boy. I have no control. I was working a few minutes ago. I'm trying. Nothing is happening. Let's see. What else to do here? There, finally. Now it's probably going to go through 20 slides all at once. So we're talking about the Anthropocene. And if you're not familiar with that concept, it's basically the era in which humanity is a geological force of the same scale as the atmosphere, the oceans, and other major systems. I'm going to start out by posing you a couple of questions. You could take your own guesses, and then I'll answer these later. So this is just kind of for fun. How much prehistoric plant matter did it take to make a gallon of gasoline? And here are 4 choices. So you take your guess and you hang on to that. Here's my second question for you. if we were making gasoline the same way it was, that is petroleum, the same way it was made in geological time, how much plant matter would it take to power the world for a year? And here you, again, you have some choices. Make your guess and hang on to it. We'll come back to that. So I'm going to talk about four things. I'm going to talk about the idea of technometabolism. I'm going to talk about how technology, the technosphere, what Debjani mentioned, I'm going to use that idea, how it consumes the historical and geological past. We'll talk about the idea of technology as it comes up in Stuart Brand's book, The Long Now. I'm going to tweak that idea in a few ways. And then we'll talk about how it's consuming our future. So what's technometabolism? Better dispense with this control. So this is what's known as net primary production. This is a data-based map of land surfaces around the world over a number of years. What you see is that, of course, every year, the sun comes out, plants grow, later they die later in the season. And every year, a certain amount of vegetable matter is produced that way. That's net primary production. This also happens in the ocean, of course. Plankton and other aquatic plants also grow on cycles like that. And that's also part of global net primary production. So then the question is, how much of that primary production do people take out of the natural system or the agricultural system, which is a quasi-natural? And what you see here, the dark red areas are places where 60, 70, 80% of the vegetation produced in a given year is taken by people. Or this map can also reflect changes in land use that mean that that area is not able to produce as much vegetable matter. And there's a little bit of fire in here too. And you can see that in the great agricultural zones of the world, the Midwest of the United States, around Europe, and especially on the Indian subcontinent, you have enormous amounts of the plant matter produced being taken out of the system by people. So that's human appropriation of net primary production. Now let's get to the idea of the technosphere. The concept, there are several great papers by Peter Half, one of them is cited here, but there are others. They're really amazing papers. He's trying to quantify this idea. And the concept is sort of that we have an atmosphere, we have a biosphere, we have the hydrosphere. We also have a global system that he is calling the technosphere. It consists of all the communication, transportation, other systems, including people. So he's counting people as part of that system. And it's important to hold that in mind because this is not just technology in the sense of devices, right? Technology also in the sense of organizations and human action that makes those the material systems work. So they metabolize fossil fuels and other energy resources. They ingest materials, they create things with them, and then they generate waste. That also happens in the biosphere, but in the biosphere, most of the waste, nearly all of it, in fact, is recycled by bacteria, and so on. So how big is this thing, the technosphere? Well, let's compare it to the biosphere. So we were talking about net primary production. Photosynthesis creates about 90 terawatts of biochemical energy each year. The technosphere consumes about 27 terawatts, so almost a third of what's produced by photosynthesis. Some of that is photosynthesis in the form of agriculture and forestry, but the rest of it is provided by fossil fuels, nuclear power, renewables, and other energy systems. This thing now weighs more than all the living matter in the world. Okay, so there's the concepts Let me talk about time and technometabolism. These fossil fuels are called fossil fuels because that's my son. I can't stop him. Luca, stop it. So, this is ancient plant matter, mostly. Some of it is animals that lived and died and then rotted and became buried under piles and piles of other material, eventually under rock and crushed down until it became coal. And I'm really only going to talk about coal, but the same thing is true of oil and so-called natural gas, which is better termed fossil gas. So most of the coal that exists was created in a single 60 million year period between 359 and 299 million years ago. That was the Carboniferous era, enormous plants, lots and lots of rotting going on. Now I'm going to do some things with numbers that are really imprecise, but the only thing that's important here is the orders of magnitude. So units are going to be converted without a lot of discussion. So down at the bottom, you can see that coal has been accelerating since the middle of the 19th century, consumption of coal. And during that period, according to our World in Data, we've consumed about close to 2 million terawatt hours. Of course, a terawatt is a trillion watts, so it's a whole lot of energy. That comes out to about 210 billion tons of coal. So the remaining reserves that we can access, not all the coal in the world, but the ones that we can, stuff that we can access, is about 1,000 billion tons. We add in the 200 billion tons that have already been consumed, we get a total of about 1,284 billion tons. That's 1/6 of all the accessible coal in the world. So if we just take a rough order of magnitude guess, this very conservative, that's between 1 and 5 million years worth of coal. So we are consuming the photosynthetic past of the planet. If we look at it in terms of what's left in the ground, so all the yellow bar there is the resources available, but the thing we're interested in here is the reserves that have already been identified. In any case, there's quite a bit of carbon still in the ground. And these on the top, you see how much of that carbon we are releasing into the atmosphere and will release over the course of the 21st century. Now, my point here is that this is a species level timescale. It is far beyond Homo sapiens. It's only been around for about 200,000 years. The scale on the left is scales millions of years. Our most distant ancestors, the early hominins, about 7 million years ago. Most of the Homo species, the Homo habilis, Homo rudolfensis, are date to at most about 3 million years ago, and Homo sapiens sapiens about 200,000 years ago. So we are consuming a past that is deeper than our own past, and goes back into the pasts of our ancestors. This is a global temperature data up through the present, but I invite you to see this as that metabolism in action. This is the oxygenation of carbon from the distant past at an incredible rate. And as you can see, it produces geological scale effects. I mean, everyone here already knows that. Not a pretty picture. Okay, let's talk about technology for a bit. It's like a close to million-year time scale here. So we have carbon dioxide concentration, a global measure, and Antarctic temperature, which is a local measure, not a global one. That's important, but not really for me, but we could talk about it later if you want. So what we see here is that during the lifetime of our species, again, I've lost control of the slides. It'll come back in a minute. But you can see about the 200,000 year mark where our own species began in deep time. And waiting for the slides. If you look up on the right, this slide is some years old now. We are at about 420 parts per million of carbon dioxide now. So far higher than it has been in the past of our species, higher than it's been actually in 3 million years. And advance. I wonder if that's interesting. That might be. No. Yes, maybe so. Thank you. Okay, so there's the past of our species. Here's where we are, 420 parts per million of carbon dioxide today, higher than in the past 3 million years. If we zoom into a scale that's more like just our own species, Homo sapiens sapiens, we see that, in fact, most of our past has been colder than it is today. So our bodies have literally evolved in a colder climate than the one we experience now, and a much colder climate than the one we're about to experience. And the interesting thing about this to me is that little bit out at the end, the Holocene era, the current interglacial era since the end of the last ice age, and how incredibly stable that temperature has been. So one way to think about this is to use Stuart Brand's concept of the long now. So Brand says, this is a 20-year-old book called The Long Now, Clock of the Long Now. He says, you know, it's been about 10,000 years since the dawn of agriculture. Here we are today in our current civilization, and what we tend to think of as technology is just that. I actually had a friend, and you know this person, is Rick Zinman, worked at Apple Computer, and you know, I'm a historian of technology, so I said to him one day, you know, what about technologies from the 1800s? He said, well, we haven't really had technology since about 1960. Like, you know, so that's the computer people mindset. That's the digital mindset. There's another way of thinking about technology, which is maybe industrial, the Industrial Revolution, or take it back further to urban technology. So the first large cities, you know, come up around 4000 BC, and everyone's familiar with the amazing achievements of the Egyptians and the pyramids and so on. But even further, we could really think about agriculture itself as the most fundamental technology of what we call civilization today, you know, and things that seem very simple to us, like ceramic vessels that can hold seeds and keep them safe from predators and store surplus for a coming year. That's what permits the growth of populations and the concentration of people in a city. So those are all ways of thinking about technology. And Brand says, let's think about that. But really, we have to see this in the context of that Holocene interglacial. A lot of this stuff couldn't have happened before that because of the ice. Some of it might have happened, but didn't. Brown says, let's think about now, not just the past 10,000 years, but the next 10,000 years. So the project to build a clock that would show time on that scale is this idea of the clock of the long now. And this is an actual project. I'm not sure whether it's ever been completed. It's sort of difficult to find confirmation of that, but it was being built in the Nevada desert. The idea is, let's have a clock that'll chime every century. And we'll think about time at a much longer scale. So we would write dates with an extra 0 to say to ourselves, essentially, the future is much longer than we think, and we are still at the beginning of a technological future. All right, now let's look at what's happened during that very short period of industrial civilization, the last 200 years, just 200 years. And now we'll focus in on what's happened in the last 70 years since about 1950. These graphs are all over the place, easy to find them, easy to criticize them too. I won't do that right now. The point I want to make is that in terms of trends in the Earth system related to our technology, all kinds of variables have been increasing at an exponential rate since that period. A lot of that's driven by human factors, such as the growth of population, growth of GDP, the economies we live in now. All of them exhibiting a sharp upward trend since about 1950. This is known in the Anthropocene literature as the Great Acceleration. In the USA, we can see this very clearly in terms of our consumption of fossil fuels, the white parts of these charts, a lot of it imported, and then also of minerals and metals. So mining, massive activity, especially of the industrial age. So can we really imagine these trends continuing for 10,000 more years? That's not going to work. We can talk later about what the tech billionaires, who are partly people I get funding from, what they think about this future. A lot of it involves escape fantasies. They're going to go to Mars, they're going to go to the moon, they're going to go to the stars. I've actually heard people say, what will we be doing in 1 trillion years? I like to say, no, not happening. We're not going to be here. Okay, now it's time to answer your questions. Okay, so how many vote for 780 pounds? How many vote for 32,700? Everybody's going to go for the top. I can see 196,000 pounds. No takers? Yes, okay. And 1,300,000 pounds. Just because. Okay, well, the minority is right for once. 98 tons of buried plant matter to make a single gallon of gasoline. So if we were doing this today, that would be 40 acres of wheat, including the roots, all to get your car to go 30 miles, if you're lucky. What about the other one? If we made it from scratch, how much of the yearly production, of net primary production, how much would it take to power the world for a year, all forms of energy? Okay, 60%, 300%, 5,000%, 40,000%. You win. 400 times. And this calculation was made 19 years ago, so that number is probably higher today. We use the fossil fuel equivalent of all the plant matter that grows on land and in the ocean over the course of a whole year. Actually, about 16 months worth then, let's call it 1.5 years today. So every year, we burn 400 or 500 years worth of total planetary production. All right. Now let's talk, this is going to be my last section here. Let's talk about how technology consumes the future as well. And this is going to be more familiar to you, but let me frame it in a way that might not be so familiar. So when we build solid, capital-intensive, long-lasting infrastructures, we make a commitment that endures in time over very long periods. So, you know, these are gigantic concrete overpasses and highways. They're not going anywhere. They need to be maintained. And we commit ourselves to that, even if we don't really mean it. And that's kind of where we are with a lot of this infrastructure now. But it, you know, the whole system commits us to all of these things. You know, this is a great image. I once had saw a talk by an architecture professor at Michigan who talked about a city that was divided like this, a small Southern California city, you know, a major interstate intersection in the middle of it. And there were no overpasses or pedestrian bridges. So what this meant was the city had been zoned into, you know, a utilities section, a residential section, a commercial section, and one other, and you could not get between them without driving a car, because the only way was across an intersection like that. So the infrastructures carry with them lifestyles and habits that we all are essentially enrolled into. It's easy to imagine, you know, try living your life for a month without ever getting in a vehicle. Try living your life for a month without ever touching a piece of plastic, and so on. You can repeat this story about practically anything. So in terms of climate change, here's an interesting study. This was done a while ago now, back in 2010, so it's already old. But they asked the question, what would happen if we just stopped building new fossil fuel infrastructure and maintaining all the infrastructure that exists? Just let it be used until it wears out and then stop. And what they found was that just doing that would effectively keep us below that 1.5 degree threshold that we've been all talking about. Of course, that didn't happen in 2010, hasn't happened today. There has been recently a movement, began sort of out of nowhere, to stop building new gas stations. I think that's brilliant. You know, just stop, just stop. So, where are we today? Back in 1957, we started measuring carbon dioxide. It was about 315 parts per million then. We're at 420 parts per million now. And except for the year 2020, when the pandemic began, there's a little bit of a dip. But except for that year, every year since then, the amount of carbon dioxide we're putting out has gone up, despite all of this climate so-called action, of which, you know, I've even been a part. We have known about this problem since the 1950s. Edward Teller, one of the giants of physics and a sponsor of the hydrogen bomb, was warning people about climate change in 1957. Roger Revelle, an oceanographer, many others, they knew about this problem. They didn't have a great grasp of all its details, but they understood the essential physics, and nothing has changed since then. Now, what happens to us if we reach doubling of carbon dioxide? So pre-industrial, before 1750, about 270 parts per million. Doubling is about 540 parts per million. 2022, we're at 420. We're up 150 from pre-industrial. That means at the current rate of increase, we will reach doubling around 2050. And when I started working on this issue back in the 1990s, that future where carbon dioxide was doubled seemed very far away. And the doubling of carbon dioxide became a kind of scientific benchmark. So every study that looks at climate change asks, what happens if we hit carbon dioxide doubling? And here are answers going back to 1979. You see they've been very consistent since then. 2.5 to 3 degrees, best guess. An important thing to notice about this chart is that the 2021 IPCC trimmed a whole degree off the bottom of the range, but kept the top. So 2.5 to 4. So the low end, the optimistic version, not happening. And the most likely equilibrium sensitivity on doubling, 3 degrees. So we have some climate policies. The climate bill that just passed is great. Lots of good stuff in it, but not nearly enough. It's just the first action the US, major action the US has ever taken on climate policy. But all kinds of commitments have been made around the world by different nations. They're, in the IPCC and Framework Convention process, they're known as independent, nationally determined commitments. The thing is, they're just commitments. They don't mean anything until they're actually executed. And what we already know, and I went through this when I was on the IPCC through last year, what we already know is that the commitments that have actually been executed so far are not sufficient to keep us to even 3 degrees. If we had no climate policy, and that could still happen again, because any policy can be changed or reversed. We're in this age of nationalism, war, all kinds of shortages of water and food. All those things can add up to conflicts about policy and changes in policy to go back and still use that buried carbon in the ground. What's coming? Well, it's not fun to talk about this, but we have to talk about it. So this study actually might have even a higher result if it were done again today. On the left is what's probably the most likely climate scenario. On the right is the extreme no policy scenario, but in both cases, we hit a point where the far right of that scale is 35 degrees centigrade wet bulb temperature. It's a different way of measuring temperature than the one that we're used to, and it's valuable for measuring temperature in humid conditions. So at 35 degrees wet bulb, people's bodies can't get rid of heat. So you begin to cook internally. If you hit 36, 37, 38, it's like going into a steam room and just staying there. So what this means is that, if you look out on the right-hand side of the Indian subcontinent there, you see some of these very extreme temperatures being reached. If this were to happen for days or weeks on end, many people who live in those places would simply die of heat because they don't have air conditioning. It's not possible to get rid of heat by sweating. And maybe you can use water to cool yourself a little bit, but the water itself will be good heat too. And then you lose that capability also. Sea level. So this is the city of Shanghai, glittering city. Here's what the map of it looks like. Sea level rise at 3 degrees after time has passed to allow the rise to happen. It's mostly underwater. This is Miami, South Florida. My daughter grew up here. Her mother lives there. Here's what that looks like now. Here's what it looks like at 3 degrees. So my advice is not to buy real estate in Miami or anywhere in South Florida. The thing about sea level rise is it takes a long time because things have to melt. We've seen really extreme melting recently in Greenland and around the Thwaites Glacier, the so-called Doomsday Glacier in Antarctica. It's just kind of hanging on by a thread. They soon begin to slide into the ocean. So the sea level rise, even that we were talking about in 2021, is probably going to be higher than we thought then. So over time, at 2 degrees, if we were able to stay there, we'd still see on the long time scale 8 to 13 meters of sea level rise. If we hit 4 degrees, we're talking inundation of large parts of the continents. The most depressing thing about this is that if we were able to somehow stop all our greenhouse gas emissions tomorrow, this long process of the ocean coming into equilibrium with the atmosphere means that we would still experience climate change for hundreds or thousands of years. Carbon dioxide lives a long time in the atmosphere, so it would basically never come back to the concentrations we have even now. And that's why the sea levels would continue to rise. Now, this is not the only piece of technology that acts like this. Fossil fuels. We look at nuclear waste, just as one of many possible examples. It lasts a really long time. The high level waste from the cores of the reactors, it takes somewhere around 9,000 years for that spent fuel to come down to a factor of 10 beyond natural uranium, or even 50 and 300,000 years before all its radioactivity is gone. So it's interesting to look at this image, which is now kind of old. This was done back in 1993. And they're starting to talk about the long-term waste storage problem for nuclear waste. They started to say to themselves, well, what about people in the far future? How do we keep them from digging it up? They might think there's something valuable in a secure storage space and try to get in there. They might not speak a language that we know anymore. They might not have writing. All kinds of things could have happened to them. So what can we do to tell them that this place is dangerous and they should stay away? There were many ideas generated. This is one known as the spike field. You just make it look really scary and thorny and assume that people will stay away because of that. So the punchline here, if there is one, is just that the past that we had in the 20th century and the 19th century, we created all kinds of things, including what's happening with our atmosphere. We created these things and we committed to them without perhaps really understanding what was done. So that 20th century is going to be with us for hundreds or thousands of years. We have taken the future and fixed it in our infrastructure. And that's why we're in this phase we call the Anthropocene. So I'll stop there, and I'm happy to talk about any of this or anything else that I do.
Thank you. So we have plenty of time for responses, comments, questions, and Isabel, you'll be monitoring. Yeah. Let me thank you so much for just kind of bringing home and making so vivid our worst nightmares. That's the first place. But you know what? One of the graphs I found very interesting was they're all interesting. The existing fossil fuel infrastructure.
Sure.
We'll go back to that.
Yeah, sure.
Yeah. So the existing infrastructure from 2010 appears to be tapering.
Yeah, it's wearing out. So
it's the wear. I wanted to
yeah, right.
Or is it just about where?
No, it's wearing out. So they're talking about things like oil tankers and gas stations and things like that. We just don't fix them when they break.
Right. And so could you that to the future infrastructure?
Well, so the global fossil fuel infrastructure is worth about $15 trillion. All of it has a lifetime. It wears out and has to be replaced. So these, really expensive things like pipelines and tankers and oil refineries and so on, eventually, lots has to be done to them. So you can think of it as, 40 or 50 years, we have to spend, $10 trillion to kind of keep it going as it is, just because we have to replace stuff that wears out. So if, some of it would last a lot longer of its own accord, but a lot of it would wear out sooner. And, if we counted the cars as well in this infrastructure, hundreds of millions of them, one thing that's been done very effectively in some places for air pollution is to have government buy up old cars, because the old cars are much more polluting than newer cars. And that all by itself can have a big effect. So I'm kind of not sure where I'm going with this anymore, but did that get at your question at all?
Yeah, sure. Yeah. Future, which is not so much the future infrastructure anymore, in terms of, say, just to take an example of, making EV much more usable.
Yeah.
Of course, the climate bill here is going all out.
Yeah.
To kind of shore up that infrastructure. And I know, having lived in other parts of the world, that there is a lot of work happening.
Yeah.
In cities, just building this infrastructure. In fact, many other countries are probably a little more advanced than the US for this matter. But that too is not carbon neutral. None of that is carbon neutral.
Yeah.
So there is this assumption that, that in some senses our lifestyles can continue if only we change them all. Only we and I'm just curious, among humanists, when we talk, or say philosophers or ethicists, when they talk about the way we live now, the problems of dwelling now, we talk about these radical kind of lifestyle changes in the way we imagine how we will dwell, which is not very much where the techno-scientific community is at in our conversations with them.
Yeah.
And that's a real kind of disconnect. Even with these mega grand millions of dollars that universities invest in these grand challenge investments, I'm talking of even UVA, where I think about $60 million has gone into sustain, the Environmental Sustainability Institute. But it's so completely techno-science in terms of solutions, if not most of it.
Yeah.
So could you give us a kind of a comparative sense of conversations happening in Stanford, which is a much more technologically kind of, techno-optimistic scenario there? They kind of think that the world, they have the answers to.
Yeah.
It's just it's a very large question, I know. But how do we even begin to push that?
Right. Well, it's solutions to climate change, there's no magic bullet. There are so many things that need to be done, and so many things that can be done and actually are being done. But the fundamental question you have is like, what about our lives, our kind of way of life, the one that we're committed to with all these infrastructures, the one that got me here yesterday on an airplane, which I have to come here anyway because I'm getting medical treatment, but it's I still feel tremendous guilt about that. Yeah, it does seem that most people in engineering and technoscience are really focused on how can we just keep doing what we're doing, only with electricity instead of gasoline, renewable power. And there's a lot of good news on that front. 80% of the investment in the world last year in energy, 80% of the new power supply was from renewables. Fossil oil and gas are just going down. They're expensive. They're going to get more expensive, and renewables are cheap and going to get cheaper. There have been estimates that we could actually redo the entire energy infrastructure of the whole world in a few years and save money by doing it, save a great deal of money. So that's why, in part, the Inflation Reduction Act was called the Inflation Reduction Act, because it does bring down, ultimately, the price of energy for most people. So that's all good. But as you say, we're still mining minerals, we're mining iron ore and lithium and all the other elements that we use in renewable systems. They go after breakthroughs that, one happened recently. They found a way to do without rare earths for wind turbines, which is great, because that's been a real issue of not just a mining issue, but a political issue. So, changing lifestyles, really, in a lot of ways, the lesson of this is that what it means is changing infrastructure. The electric vehicles are a kind of cosmetic fix, because they're still all individual vehicles, and that mode where we're all independent, we don't use public transport, we do everything by ourselves, that's still the dominant image of where we're going. Yeah, well, let me stop there and see what else people want to talk about. Yeah.
The question about the different kind of infrastructure, what your other book is about, the infrastructure required to even get to producing visualizations like this that have such rhetorical impact. How would you describe the condition of knowledge, the substrate upon which these observations are made? In other words, is there a sort of a major foundational database that is hard to access, or there are data records that I could interrogate, for example, and generate my own visualizations? How is it set up? How does one access the actual data and models, and sort of an audit trail, right, by which you get from data to that?
Well, that's a whole other branch of work that I've done and many of my colleagues have done. A lot of the graphs I've used here are from Our World in Data, which makes the raw data available. You just go to the site and download it it's there along with the graph. As you know, a lot of journals now require data deposit along with articles. That system sort of works. I mean, every time we look at it closely, we see that it's, like 50% working, but a lot of it can be gotten that way. Climate models and climate data, there was a big struggle back in the between 2000 and 2010 not over data itself, but over opening up modeling and algorithms for everyone to look at and use. And that was pushed by climate skeptics and eventually resulted in a sea change in climate science, where all of that stuff is now available from the Program on Climate Model Diagnosis and Intercomparison at Livermore Lab. You can get the models themselves. You can even get stripped down versions that can be run on a PC. I mean, most of these things are run on giant supercomputers, so you wouldn't be able to use them anyway if you could download them. But the stripped down versions can do most of the same job. So does that get at what you're interested in? Yeah.
There's a speed of anger described 10 years ago, so stuff gets opened up. It sounds like you said.
Yeah. Yeah. Adrian.
Thank you so much for that wonderful talk. So I was thinking about Stephanie Lemenete's book on living oil. And I was wondering if you could reflect a little bit on how infrastructure and culture come together, and sort of just thinking about that relationship. One of the most striking moments I thought in that book was where he describes like walking in flip-flops on hot asphalt, smelling the gasoline that you're putting in your car, touching the wheel, turning on the engine, and all of these embodied experiences that for her say like summer vacation, or I have a sort of moment of freedom as a teenager. That essentially like a lot of the infrastructure that is causing deep negative planetary effects are actually imbricated in a cultural nostalgia that is hugely positive for so many of the people who are embedded in the infrastructure. And that to sort of move from a sort of positive, embodied, affective relationship to that infrastructure to one in which that infrastructure is seen as having this net negative effect is actually a push against a deeply embedded set of cultural webs that people are enmeshed in which they understand that the climate is changing, but their entire sort of media consumption that has formed their entire lives have told them that those feelings feel good. Mm-hmm. And I thought that that was a moment in her book that was so smart. And it's something that I wonder if you wanted to sort of go multi-scalar, right, on this big picture you presented to us. But how people actually feel infrastructure and move their bodies through infrastructure often has very different cultural implications.
Really well said. I think you answered your own question in a way, but let me spin on it a little bit. So how many people here like hot sauce? How many people here liked hot sauce the first time you tried it? Kind of burns, doesn't it, the first time? And then you do it a few more times and it starts to taste good. Well, they've done this experiment with dogs where they try to get dogs to eat things that have hot sauce on. The dogs will not eat it. They just won't do it, right? So they're smarter than we are. I like hot sauce too, by the way. But the point is that you can become, by virtue of repeating an experience over and over again, you can not only come to get used to it, but actually to enjoy it. And the same thing, goes for everything you were just talking about. I mean, gasoline doesn't smell good as a just kind of objective fact, and yet it can still provoke feelings of nostalgia and sure.
Yeah.
Chime in.
Thank you. I'm Charlotte Rogers. I teach environmental humanities this year at the University of Virginia, and so I really wanted to ask a similar question that maybe pushes back against what Adrian was just mentioning, because I'm a scholar of environments and cultures in Puerto Rico, which was hit with a hurricane, only Category 1 last weekend, but there's flooding has been catastrophic, and people in my network say it has had a re-triggering effect from the traumas of Hurricane Maria, right? And so it's an island that is bearing the brunt of the more powerful and more frequent storms and the rising seas that we're seeing, but it also has an incredibly weak and decaying infrastructure. Particularly the electrical grid has been privatized but not modernized. So it's kind of an interesting, I don't want to frame the Caribbean as a laboratory for experimentation, but it is a picture at the moment of what would happen. What are some ways that we can change that affective relationship with infrastructure? And the communities that I follow in Puerto Rico are no longer nostalgic for fossil fuels and electrical grids that run on wires, right? So there is a huge push towards like solar energy and towards reducing energy usage by the people who are bearing the brunt of climate change. So I wonder if your research has moved to expand maybe some of the communities that are currently most affected by the global North's use of energy. Puerto Rico, by the way, is their American citizens there, although they're not usually considered in talks like this. So I just wondered if you see other circumstances of maybe pushing back against that idea of nostalgia. Even nostalgia for air conditioning.
Well, I have a couple of things to say about that. First of all, my wife was born in Puerto Rico, so I hear about it a lot. She's actually, none of her family's there anymore, but yes, I've seen the same thing that the people who got through the storm and had solar power did just fine, at least as long as their buildings were intact. And those who were hooked up to the grid are suffering. On the other hand, one of the things we see with hurricanes, I had a grad student who did some interviews in Texas and Florida about hurricane, after major storms. And one of the things she found was that people who did okay, their house didn't get wrecked by the hurricane, if that had happened to them, they were actually less likely to accept the thesis of climate change driving increases in hurricanes because they said, you know, I did fine. I'm okay. I can do it again. So, you know, it can have these really contradictory responses to things like that. But back to Adrian's question for a second, you know, another place that we see this even more radically than around fossil fuels is around food. You know, so beef and lamb in particular, but really all forms of animal agriculture contribute to climate change. Getting people to shift to another diet or even to reduce the amount of those things that they consume is really, really hard because of all things, food is the most basic to your sense of cultural identity. You know, you go around looking for restaurants, you identify them by their, you know, the nationality, and it has a cuisine associated with it, right? So, you know, I've been in places where the food that people thought of as their most central and most comforting food was to me not good at all. But for them, that's what they want to consume. And, you know, same thing with you know, Americans now. I mean, when I talk to students about beef, I see them just shaking their heads. No, not going to do that. Not going to change that, of all things. So.
How interesting that your talk privileged metaphors of eating.
Of eating?
Of eating.
Yeah.
And now we've found our way back to it.
Yeah.
I wonder if another version of your talk could graph people's gustatory entitlements as a kind of cultural infrastructure.
Yeah.
I don't know what it would take in order to convert the data, what the data would consist of, how you'd get it, but how interesting it would be if there were overlays that had to do with, say, entitlement, the rights. What would a graph of human rights look like as against this? Because nothing is clearer from your talk that the two are intricately intertwined, and until you've addressed the latter, not much is going to happen with the former, namely what you have shown us, right?
Yeah.
So it's really kind of a question of the fostering, as an event like this does, dialogue and I would say activist collaboration among people from different fields.
Yeah. Yeah. Well, another way to slice it that I haven't done at all here, slice it, yes. Yes. I'll think you like your slices. Another way to slice it is in terms of income. So, you know, 50% of the climate impact in the world, it comes from 10% of the population. The 1% have an enormous impact just on their own. And the tiny fraction of people who are billionaires have an even larger footprint than the wealthy among us. So there's a way in which, you know, one of those graphs there shows rising population. And we just had an announcement yesterday, I believe at the UN, by scientists saying we've got to cut back on population. And I agree with that. But on the other hand, which population? And the question, you know, the real problem is too many rich people more than it is too many people per se.
Well, thank you for this talk. I'm sitting here with a lot of questions, and this conversation has been enormously productive and also worrisome. Tell me, can you talk to us a little bit more about the role of deep time? So I'm thinking about deep time as it extends back but also forward. And so you started out your talk saying how bad we are actually at thinking about time, right? Data models notwithstanding. In the time that you've been doing this work, and you've been like observing what's being said, and maybe you could say that the climate inaction community, are we now at a point where folks accept the evidence but still doubt on time? Like they are actually not able to grasp the tangible results of the world, or they want to cast everything forward? Because you know, among the many numbers I wrote down from your talk is that we have remaining coal reserves of 1 to 5 million years worth. So if I'm already inclined towards inaction, that could help me to solidify that position. Take one example out of the very rich and detailed thought. So I wonder if you could tell us a little bit more what you're thinking about time there. Are we ever going to win that one?
So first, let me just say the 1 to 5 million years is that's my estimate of how much of past coal we have already consumed.
Oh, I see.
So there's about 5 times that much remaining in reserves. We could keep burning coal for hundreds of years. But if we kept exploring, maybe even longer. But we'd be cooked by then, so probably we won't do that. But your question is a really good one because it's, there are still lots of people around and they're fueled by, terrible people. Lots of people around who will say, oh, the climate's changed before.
Yeah.
This must be just another natural cycle. I just dismiss, 150 years of climate science with a wave of the hand because they know that the climate has changed before. And yes, it has changed before, but not on the time scale that we're talking about. So that's a critical piece that is just missing for most people. That, in 100 years, we have raised the temperature of the Earth about 1.2 degrees. That's an amazing thing historically with respect to past changes of climate. You do see a few instances in the deep past of super dramatic changes like that, in a 10 or 20 year period, really rare. So, understanding the pace of climate change is the rate that really matters more than the amount. If it was 1.2 degrees over 1,000 years, then we'd have a much longer time to adapt, and so would animals and plants. So I do think there's an enormous missing piece of knowledge there for most people. And one of the reasons I began to think about this a lot is that, I've done history myself. It's, my 2 main books are history books. And yet I find that among historians, understanding of anything that happened more than 10,000 years ago is basically missing.
Not anymore.
Well, maybe not anymore. Not you guys. Yeah. Yeah, they dump it into archaeology or something like that. But, this talk is kind of aimed at stretching that horizon so that you think of the past, deep time as part of our own history, because we've been eating it.
I find this thinking, using deep time as like a very powerful way of understanding the scale of the problem. But I wonder if you see a tension between this kind of discourse of deep time, and then on one hand, understanding climate as a political problem on the other. So in terms of thinking of deep time, you sort of think of like species scale,
yeah,
right? And the Anthropocene as like a human artifact. And if we take that as the narrative, like the enemy is kind of the human being, I feel like you could easily fall into, thinking about overpopulation, right? But as you point out, like the problem is actually a certain kind of political class, and a problem in our political economy. To me, like the deep time also kind of depoliticizes, or has a danger of depoliticizing the problem and kind of like abstracting away from the political economy that we exist in, that perpetuating the problem. Does that make sense?
It does. I would go back at you on the infrastructure side of this, not the deep time part. I think you're right about that. But, a lot of the discourse about climate is either it's infrastructure or it's policy. And the point I'm trying to make here is that infrastructure is the policy. So the existing infrastructure is the policy. I can't say that too many times. So that it's not, people think of policy as something that happens in Congress. We pass a bill, we send out some money, and yes, that can matter a lot, and we need it. But just flipping over to we need better policy doesn't really recognize the commitment that's already there And all these things like the habituation to it that we have, the investment, the emotional investment we have in it. So on a personal level, but also on a political level, we have these commitments that are enormous and really mostly unrecognized because we think, oh, we can change the policy, that'll fix things. And yet the time scale of the fixing is decades or even centuries.
Yeah, we have some.
Oh.
Thank you.
You're welcome.
Great talk.
Great question. Thank you.
So there's our colleague Enrico Cesarati come, but he led our environmental humanities initiative for Harlem. He says, thank you very much for this informative presentation. We usually tend to think or not think at all the past and the future as our ways of life in Antiquity. I'm wondering if you could say something about how technology and the technosphere might possibly help shift this way of thinking that has brought us to the catastrophic situation you're so fortunately depicted. That's again your whole talk.
Right.
But if you just have a...
Well, there's a piece toward the beginning there that I like.
Yeah, he says that we usually tend to not think at all of the past and the future and our ways of life in anthropocentric terms. It's not very clear. Yeah, okay.
Yeah, I'm kind of not sure what to do with that. So if you're still there, make another comment and we'll see if we can get to it.
There's our, someone said, oh, this is about technology and technosphere with my technology, something different. But if I just towards the end, given that this is a series on futurities, one public intellectual, Roy Scranton, a few years ago wrote a book on learning to die in the Anthropocene.
Yeah, I know that book.
Right? Now, I'm not going to go into his arguments. It's a different context altogether. But I just want to pick up the idea of extinction that appeared in your abstract.
Yeah.
People talk in terms of this doomsday scenario. So the very, very language in which we talk about the doomsday now, the ground has shifted in some way. So you have Roy Scranton saying learning to die in the Anthropocene does not mean mass extinction of human species, but how we learn to kind of live with the death of our way of living in modernity in the past 200, 300 years. And the importance of learning, accepting that that kind of death. That is one way to imagine what is coming to an end, because this is a kind of language about some kinds of endings. Okay, so when we think of futures, we no longer think in terms of an apocalypse that's awaiting us sometime in the future. The idea is that temporally speaking, we are already kind of in that spiral in many ways. And in some ways that's irreversible. So do you have any final thoughts about thinking about, technology, technometabolism in terms of this new coding of extinction?
Yeah. Well, I mean, so the first thing I'll say is that, I run an existential risks group. I almost always say, I don't think anything that humans will do will necessarily extinguish every single human, not even a nuclear war or nuclear winter. Some people would probably make it. But what you're saying is the extinction of the industrial way of life. And I think that's a very real prospect, not in the really near term, not in 10 or 20 or 30 years, but in a few hundred, sure, And the reason I think that is that there are all kinds of unknown unknowns, especially about ecological systems and how they will respond to extreme climate change. But every time we find a new phenomenon, it's usually bad. We're not finding that lots of things are getting better in any sphere that we look at of the biosphere. So will we be able to persist with the kinds of lifestyles we have now? Well, millions of people are hard at work trying to make that happen. So maybe, but we're already committed to probably 2.5 or 3 degrees of climate change. And if we don't make really radical policy changes really soon on a global scale, it's going to be 4. That's really, there's this book, The Uninhabitable Earth, which is a bit exaggerated, but if you start to look at the high ends of the scenarios we have,
Bill Stephan called it the hothouse Earth, right?
Yeah, hothouse Earth. If we just look at the this again, 2.5 to 4 degrees on carbon dioxide doubling, we're going to reach that around the middle of this century. We probably will reach it no matter what happens now. So let's say it's 4 degrees, because that's what the range means. Could be 4. The range also has tails that are excluded here. This is like the 95% interval, but there's a tail that's even higher than that. And many of the models that were used for IPCC 2021 did produce higher temperatures. And there's a lot of questions about why that happened. This estimate is not based on those models, partly because they were suspicious of those results. But people have spent decades getting to the point where models produce that result. So why is that happening? Maybe there's a reality to it. So maybe it's even more extreme than this. And I don't like making these prognostications in any way. I've got a child who's 19 years old and will probably still be alive near the end of this century. Yeah. So.
And to be clear in the argument here, if we come to the end of our industrial lifestyle in a couple of years, what's next is not as it was for our previous ancestors who could enjoy the bounties of the natural world to sustain themselves.
Right.
So we'll not really not have these technologies, right?
Yeah.
This is like tech eating the future.
Yeah.
But then we're down pretty considerably in the natural resources department.
Exactly. One of the things that people used to say back in the Cold War was that if we bombed ourselves back to the Stone Age, we would never get out of it again, because all the easily accessible energy sources and minerals have already been mined. So we were very lucky to just come along and find these things lying around waiting for us, millions of years of planetary history. But we won't get that chance ever again. So they would probably find other things to do, but it wouldn't be this kind of society.
I think, yeah, please join me in thanking.
Okay. Thank you. Thank you so much.